Let me ask you something simple. What does it actually mean for two things to be isolated from each other? Your first instinct is probably something like, they can't affect each other, they're separate. There's a wall between them, and in everyday language, that's fine. But in computing, and especially in cloud computing, that definition is so incomplete that it's almost dangerous. Because here's the thing. In the last video, we saw that during Spectre and Meltdown, the hypervisor correctly isolated virtual machines from each other. The network boundaries were intact. The memory address spaces were separated, and yet, one tenant could still extract another tenant's cryptographic keys. Every isolation mechanism was working, and isolation still failed. If your mental model of isolation is just, there's a wall, you have no way to reason about how that's possible. The wall was there, it was real, something else went wrong. So in this video, we're going to build a better mental model, one that actually lets you think clearly about what you have, what you're missing, and where your exposure lives. Isolated is one of those words that sounds precise, but isn't. When a cloud provider says your environment is isolated, they're not lying, but they're also not saying what you probably think they're saying. They're describing a property of one specific layer of a system that has at least 4 distinct layers, each with its own definition of isolation, its own mechanism for enforcing it, and its own failure modes. The mistake most engineers make, and I'd include myself in this at one point, is treating isolation as a single binary property. Either your workload is isolated, or it isn't. Either the wall is there, or there's no wall. But that's not how any of this works. Think about a block of flats. Your flat has a front door with a lock. That's one layer of isolation. It has walls that don't transmit sound very well. That's another layer. It has a separate electrical circuit. Another layer. A separate water meter, another. Now imagine someone says your flat is isolated. Are they talking about the door, the walls, the plumbing, all of them? Because those are 4 different claims, with 4 different implications, and any one of them could be true, while the others are false. Cloud isolation is exactly like this, and the layers matter enormously. Let's walk through them. From the bottom up, the first layer is hardware. At the bottom of everything sits physical silicon, a real CPU, real memory, real network cards, shared between dozens or hundreds of virtual machines simultaneously. At this layer, there is no isolation in the traditional sense. The hardware doesn't know which tenant's workload it's running. It doesn't enforce boundaries between them. It just executes instructions as fast as it can. What exists at this layer instead is resource scheduling. The hypervisor tells the hardware what to run and when. But the hardware itself is a shared, undivided pool. This is not a design flaw. It's the entire economic premise of cloud computing. Shared hardware is what makes it affordable, and as Spectre and Meltdown showed us, shared hardware means shared physical state, including state that software isolation mechanisms can't see or control. The second layer is the hypervisor. This is where the most familiar form of cloud isolation lives. The hypervisor is the software layer that runs directly on the hardware and carves it into virtual machines. Each VM gets its own slice of CPU time, its own allocated memory address space, its own virtual network interface. At this layer, isolation is real and meaningful. One virtual machine genuinely cannot read the memory allocated to another virtual machine through any normal mechanism. The hypervisor enforces this. When you hear someone say that cloud VMs are isolated from each other, this is what they mean, and they're right, at this layer. What the hypervisor cannot control, however, is the hardware beneath it. It manages the allocation of physical resources. It cannot change how those resources physically behave. That's where the Spectre vulnerability lived. Not in the hypervisor, but underneath it, in the silicon, the hypervisor was sitting on. The third layer is the operating system and process boundary. Inside a single virtual machine, your operating system provides another tier of isolation between processes. One process cannot read another process's memory. System calls go through the kernel, which enforces access controls, file permissions, user namespaces, capability restrictions. This is a whole ecosystem of isolation mechanisms, each with its own guarantee and its own surface area for failure. Containers operate primarily at this layer. When people say containers are isolated from each other, They mean that the Linux kernel is using namespaces and C groups to give each container its own view of the file system, its own process tree, its own network interface. That isolation is real, but it's kernel-enforced, which means its strength is entirely dependent on the correctness and configuration of the kernel itself. This is worth saying clearly. Containers on the same virtual machine share the same kernel. They are not isolated from each other at the hypervisor level. A container escape, a vulnerability that lets a process break out of its namespace, drops you into the host VM. The hypervisor layer is still below you, but you've defeated the layer you were relying on. The fourth layer is the network. Network isolation is probably the layer most engineers interact with most directly. VPCs, security groups, network ACLs, private subnets, these are all mechanisms that control which network traffic can reach which workloads. At this layer, isolation means your workload cannot receive unsolicited network connections from outside the boundaries you define. And with proper configuration, this is strong and reliable. But notice what it doesn't protect against. It doesn't protect against a compromised workload inside the same VPC. It doesn't protect against vulnerabilities at the application layer. It doesn't protect against the lower layers we've already discussed. Network isolation is the most visible layer. It's also the easiest to misconfigure. An overly permissive security group, a missing subnet rule, a misconfigured peering connection. And because it's visible, engineers sometimes treat it as sufficient when it's only one layer of a much larger stack. So here's the mental model I want you to carry forward from this video. Isolation is not a wall, it's a stack. At each layer, hardware, hypervisor, OS and process, network, there's a specific mechanism enforcing a specific boundary with a specific set of guarantees. And critically, each layer's guarantee only holds if the layer beneath it is behaving as assumed. The hypervisor's memory isolation guarantee holds, unless the hardware underneath leaks state in a way the hypervisor can't see. The container's namespace isolation holds, unless there's a kernel vulnerability that lets a process escape. The network's VPC isolation holds, unless something inside the network boundary is already compromised. This is not a counsel of despair. All of these mechanisms are genuinely valuable. The stack works the vast majority of the time. But when you treat isolation as binary, either you have it or you don't, you lose the ability to ask the right questions. You can't identify which layer your real exposure lives at. You can't make informed decisions about what additional controls to add, and you can't reason clearly about what a given failure actually means. The engineers who think in layers can do all of those things. The ones who think in binaries get surprised. There's one more thing I want to sit with before we move on. You don't control most of this stack. The hardware is designed and maintained by Intel, AMD, and ARM. The hypervisor is operated by AWS, Azure, or Google. The host kernel is managed by your provider. You, as a cloud customer, operate primarily at the top of this stack. Your application, your containers, your network configuration. This isn't a criticism of cloud computing, it's the nature of the service. You get leverage, running infrastructure at a scale you couldn't otherwise afford, in exchange for control. You're trusting the layers beneath you to behave as specified, which means the most important skill you can develop is knowing precisely where your trust ends and your control begins. What you can verify versus what you have to accept on faith. What your provider has contractually committed to versus what is simply implied by the marketing language. That's the question we're going to dig into in the next video. I'll see you there.